the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is generally dedicated to linear algebra students. However, most algebra students can actually watch this video as well because they might be going through matrix computations, and this video is just a bunch of definitions about the structures of a matrix. So there's not a lot of mathematics here, it's just a lot of definitions, so let's roll right through it. First of all, when we speak of matrices, we're going to use something called element notation. So we're going to talk about the elements of a matrix, and we all just have to agree on some type of way to talk about the objects or the ordering of a matrix or the entries of a matrix. So that would be element notation. The entry of a matrix A, located in the ith row and jth column, is denoted by A sub ij. That is, if you had a matrix, for example, like this, then the element right here, or the entry right there, we would refer to as A sub 2, 4, because it's in the second row, fourth column. And this works really nicely because, well, we use the notation that A is a, well, in this case, A is a 3 by 4 matrix. So notice we always mention the number of rows first and the number of columns second. That is matching up here. This is the second row, fourth column. So the ordering does match up very nicely. A little bit of a clarification here. This actually should be a warning more than a clarification. If you're used to working with Google Sheets or Excel, the IJ notation that we're using is opposite of what is used in those software packages. For example, Excel uses B4 to refer to column B and row 4. So they actually mention the entry location in the reverse order that we would use in mathematics. And that's the same thing, by the way, for Google Sheets. So it's just a heads up, if you're used to using those software packages, then this will be the opposite of what you're used to. The next thing we need to mention, and this ends up being very important, is the idea of a diagonal entry. Now, whether or not the matrix is square, that is, if it's, for example, 5 by 5 or 10 by 10, or it's non-square, that is, it's something like what we just dealt with, a 3 by 4, we reserve the language diagonal entry for all the entries where the positions are equivalent in row and column. That is, the diagonal entries in the matrix A are A11, A22, A33, A44, and so on and so forth. For example, in this matrix, A11, A22, and A sub 33 are the diagonal entries. Now, to be honest with you, we really don't talk about diagonal entries in non-square matrices that often. And when we do, some people call them diagonal entries when actually they're not. So some people might say that these are diagonal entries, for example, but that's actually not true. It is A11, A22, A33. The column and row position must be equivalent. So this is not actually a diagonal entry. The definition's pretty simple, but worthwhile to mention. And that leads to a very important definition here, the main diagonal of a matrix. Now, when we speak about main diagonals, again, we generally focus on square matrices. So the diagonal entries in a square matrix, an n by n matrix, are called the main diagonal. For example, in this 3 by 3 matrix, the main diagonal is that highlighted diagonal right there. In fact, I'd probably write it this way. That's the main diagonal. The entries are the diagonal entries. 1 is the diagonal entry in the 1, 1 position. 5 is the diagonal entry in the 2, 2 position. And 9 is the diagonal entry in the 3, 3 position. But those form the main diagonal. Again, all these definitions are going to be important as we move forward in linear algebra, or if you're not taking linear algebra and instead you're taking, for example, a pre-calculus course that has matrices in it, it'll be very important for matrix algebra. Now that we have ways of referencing the entries of a matrix, and we've talked about the diagonal entries of a matrix, and we've talked about the main diagonal of a matrix, it is kind of nice to talk about very special matrices. A square matrix whose non-diagonal entries are 0 is called a diagonal matrix. For example, this 3 by 3 square matrix, it would be called a diagonal matrix because everything off the main diagonal is 0. That's a good way to think about it. All entries off the main diagonal are 0. By the way, a little bit of a side note, it's not that every entry on the main diagonal has to be non-zero. By definition, this still would be a diagonal matrix. In fact, by definition, a square matrix whose non-diagonal entries are 0 is called a diagonal matrix. Well, notice the definition does not mention anything about what the main diagonal entries have to be. So they could have been 0 as well, and technically, as a caveat, this would be considered a diagonal matrix. Because again, all of its non-diagonal entries are still 0. So technically speaking, this is an odd case of a diagonal matrix. Speaking of this diagonal matrix, the zero matrix. A matrix whose entries are all zeros is called a zero matrix, and it's written as, well, 0. I can't say zero matrix because it's, well, I could say it's written as 0 bolded, I suppose, but it's just written as 0. Technically, this definition does not force the zero matrix to be square, so it could be a non-square matrix, for example, a 3 by 4 or something like that. But as we saw in this previous example, it could also be a square matrix, which is more often the case, to be honest with you. Now, before I get to my final definition in this very short video, I do want to make mention of something that I don't have written in my lecture notes, but I would like to add it here. Notice in this very special square matrix that we have 0 entries all above the main diagonal. We do actually not have all 0 entries below the main diagonal. This very special style of square matrix is called a lower triangular matrix. And because we have a lower triangular matrix, we could also have an upper triangular matrix. These are essentially square matrices where you have all 0 entries above or below the main diagonal. It's lower triangular if all the entries above the main diagonal are 0, and it's an upper triangular matrix when all the entries below the main diagonal are 0. Basically, it's upper heavy. You can think of it that way. It's heavily weighted on the upper half, so it's an upper triangular matrix. The other one, the lower triangular, is heavily weighted on the lower triangle of the matrix. And these definitions only hold for square matrices. There are some textbooks I've seen that reference lower and upper triangular matrices as possibly being non-square, but that's actually an abuse. It's really not true. So we will reserve this language in the future for square matrices. It does become important, and you can probably see why. If you take a look at the upper triangular matrix here, is generally what we'd like to get to when we get to echelon form. Finally, and just because this definition doesn't fit well in any other place, we're going to talk about equivalent matrices. Two matrices are said to be equal or equivalent if they have the same size and if their corresponding entries are equal. Now, a lot of people just take this for granted. They just say, yeah, of course, that's true. But we need the definition just to be clear about it. So for example, these two matrices start by looking somewhat equivalent in size. They are both 3 by 3. That's the first requirement, that their size matches up. If you recall, I mentioned, or if you're watching my videos in order, I mentioned early on in this video series that we do not refer to the size of a matrix as the dimension of a matrix. So I'm not going to say the dimensions of this matrix are 3 by 3 because we reserve that word, dimension, in linear algebra for something completely different. So at least the size of these two matrices match up. Now let's see if their corresponding entries are the same. 1 versus pi over pi, sure, that's the same. 2 versus log base 2 of 4. If you know your mathematics, you do know that the log base 2 of 4 is actually 2. 3 versus the square root of 9, yes. 4 versus 2 squared, sure, why not? 5 versus 5 times the cosine of 0, absolutely. And then I got lazy. 6 versus 6, 7 versus 7, 8 versus 8, and 9 versus 9. These are all equivalent entries, therefore, these two matrices must be equal or equivalent. And that's purely by definition. We needed to be able to reference the equality of two matrices before we move forward in this course. Now that's all I have for this video. To be honest with you, it's not a theory heavy video at all. So I hope this helps out and it clarifies any issues you might have or questions you might have about the structures of matrices. And then in the next video, we'll go through the sums of matrices and scalar multiples of matrices. I hope to see you there. Have a wonderful day. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.